Okay, so let's do 14.8. It's called change of variables. So I'm going to make a definition. I'm going to define the Jacobian. So given x is a function of u and v, y is a function of u and v, then we define the Jacobian, written this way, is like a 2 by 2 determinant. So it's partial derivative of x respect to u, partial derivative of x respect to v, partial derivative of y respect to u, partial derivative of y respect to v. So you can write it like this. So it's the absolute value of a 2 by 2 determinant here. So let's look at an example. So here's the first example. So suppose x is equal to u v squared and y is equal to u plus v. Find Jacobian. Okay, so let's do it up here. Let's do it here. So we'll have our Jacobian symbol x, y, u, v here. So it's going to be partial derivative of x with respect to u is going to be v squared. Then partial derivative of x with respect to v, so it'll be 2uv. Then partial derivative of y with respect to u, so it'll be 1. Partial derivative of y with respect to v, which will be 1 also. Then it'll be v squared times 1. So v squared times 1, then minus 2uv times 1. That'll be the absolute value of this. So it'll be then absolute value of v squared minus 2uv. So that'll be your answer. Okay, now let's take a look at the change of variables theorem. Okay, so here's the change of variables theorem for double integrals. It says let R and S be two regions with T of S equals R, and T is a mapping from the UV axis to the XY axis, where T is 1 to 1, C1 mapping. The C1 just means the partial derivatives exist and are continuous. Don't worry about that too much right now. So it says if f is a continuous real valued function on R, we have a way to relate a double integral over R to double integral over S. So we have the same f on both sides, but here it's f of composed with our t function. And we have the Jacobian on this side also. So pretty much we're changing from xy variable here to uv over here. And we're going to look at an example. But the way this is the Jacobian guy right here, and the way you should think of that is it's like a area distortion factor. Okay, so let me explain this a bit more by doing an example. So let's look at an example. Okay, so here's our example. So say R is the square 0, 1 cross 0, 1 will be x, y. So we're going to find the double integral over R of this fxy function. So it's 2x plus 1 to the 4th y dx dy. So again, here R is 0, 1, 0, 1. It's going to be 0, 1 on the first one, 0, 1 on the second one. So let's do this without the theorem, the change of variables theorem. So the way we do it, we would say let u equal 2x plus 1, then du dx is 2, then du is 2 dx. So then dx is du over 2. Let's also here, because the change of variables we had both a u and a v, so say here let v equal y, then dv dy is 1, so then dv equals dy. Okay, So let's make these substitutions then. So this will be equal over here. So it'll be double integral. So it'll be, well, since v equals y, the outer integral will stay the same, is 0 to 1. Then the inner one will be u of 0, u of 1. That'll be your function. So it'll be u to the 4th. Now y we're calling v. Then my dx is going to be du over 2. And my dy could write it as dv. Okay, so here's my u up here. So u of 0 would be 1. And putting 1 up here, this would be 3. So we get then 0 to 1, 1 to 3, u to the 4th, v. I'm going to write times 1/2 here, I'll explain that in a second, times du dv. Okay. So I claim this will be the area distortion factor here. Distortion, which would also equal the Jacobian. I claim, well, I'll show that now in a second. Okay, and also the S region here will be 0 to 1, 1 to 3. So let's draw the S. So it's in the UV plane, say V is like the Y, so let's draw it here. So 0 to 1 on the V, so let's say it's 1 there. And then it's 1, 2, so there's 1 here, 2, 3, so drag it in here. This would be your S. And let's draw our R over here. So this is the V, and this is the U here. And let's draw our R region. So R region is here. This over here, this is the Y-axis and the X-axis. So it's 0, 1 on the X, 0, 1 on the Y. So look, something like this. So that's our R. Okay, so we have a mapping then going between them that we're going to call T. So note here, the area, let's call it A for area. Area of S, well, it's going to be the base times the height, or length times the width. So down here that's 2 because it'll be 3 minus 1, and the height's 1, so it's going to be area 2. Because it'll be 2 here and 1 here. And the area of our R region, well, just 1 here and 1 here, so it's just 1. So note then that our area of a region R equals 1/2 times the area of S. And I claim that's how we're getting this 1 up here. Alright, let's keep going. So now let's try and find the mapping T that does this mapping. So let's see, so it's T of U, V, and it's basically going to go to our X, Y, but our X up here, as right down here, I'll just bring it up here for a second. Notice our X up here, U is equal to 2X plus 1. If we solve that for X, so subtracting 1, you have Y minus 1 equals 2X, so dividing by 2, X equals Y minus 1 over 2. Okay, that's going to go in, for my X over here. So it'll be Y minus 1 over 2. And the Y just equal V, so it'll go here. So that should be our mapping here. Let's show that the Jacobian is 1/2, which should be the area distortion factor, which we've shown here. The area distortion factor is 1/2. So let's look at the Jacobian here. So I've written my Jacobian definition here. So this is our x, this is our y. So then derivative of x with respect to u, so it'd be 1/2 here if you look at this guy. So it'd be 1/2. Derivative of x with respect to v, well, there's no v in this part here, so it'll be 0. And then going on to the next one, derivative of y with respect to u, there's no u for over here, so it'll be 0. And derivative of y with respect to v, and y is equal to v, so it's just 1. Okay, so then doing this determinant, so it'll be 1/2 times 1, so you go this times that. And that times that minus. And we take the absolute value, but here it's just going to be 1/2. And you can see that's the area distortion factor, as we already mentioned, because we said the area of R equals 1/2 area of S. So that 1/2 corresponds to that 1/2, which also corresponds to the 1/2 up here. Okay, let's keep going. Okay, so summarizing, our capital T in our case then is u minus 1/2, comma v. Our Jacobian we found was 1/2, and our fxy guy was 2x plus 1 to the 4th y, got up from up here. So note here then, if I go f of t of uv, so it means, so this is my x here, this is my y. So it means go to your f function, in place of the x, we're going to put u minus 1/2, and in place of the y, we're going to put a v. So this would be then, in place of x, putting u minus 1/2, so it'll be 2 times u minus 1/2 plus 1 to the 4th. In place of v, we're putting, in place of y, sorry, we're putting a v. And notice those two cancel. And then it'll be u minus 1 plus 1, so it'll be just u to the 4th v. Notice that's equal to this guy here. Okay, so summarizing, we can say the following. So summarizing, you can say the following, and we can say the double integral over r, again r is a 0, 1, 0, 1, and in place of the 2x plus 1 to the 4th y, I'm just going to write fxy there. So it'll be f xy dx dy. We've shown that equals integral, double integral over s, where again s was 0 to 1, 1 to 3, and then it was f of t uv times our Jacobian, absolute value of our Jacobian, uv du dv. So pretty much we verified the change of variables formula for this example anyway. So you get an idea, better idea now how to use this. We'll look at some more examples, more challenging examples in the next video. So let's stop right here.